Hello my friends, welcome to the Moon. There are millions and millions of pieces of space debris flying around the planet. Most are human-generated objects, such as pieces of spacecraft, all flying around in space at velocities exceeding 7 kilometers per second, 7 times faster than a bullet. This means that even a small fragment can cause catastrophic damage to operational satellites or crewed spacecraft. The increasing frequency of space travel in low Earth orbit has caused serious concern about Kessler syndrome, a chain reaction of collisions that could make our orbital regions unusable for decades. This management of space debris is therefore a critical component of space sustainability. Satellites, as we know, are absolutely important for communication, navigation, weather forecasting, and Earth observation, all of which support life and infrastructure on Earth. Ensuring the safety of these satellites require not only removing debris, but also adopting innovative methods to recover and reuse valuable materials. My friend Daniel will now explain our proposed solution for this ominous, scary problem.
Hello, my name is Daniel and I'll be introducing the mission specifications and operational concept for our proposed project, the Space Capture and Recovery Autonomous Platform, or SCRAP, operating alongside a present satellite mission, the International Space Station. So firstly, the system will require 5 separate component entities to function. These will be, number 1, a new ISS module called Scrapyard, which acts as the main control hub and user interface. Number 2, the Autonomous Salvage Tug, or AST for short. This would be the main spacecraft vehicle platform that performs orbital rendezvous, debris capture, and transport. Number 3, one or more Autonomous Salvage Drones, or ASDs. These are smaller vehicles that perform the detailed disassembly and material recovery tasks. Number 4, deorbiting modules, or DOMs. These are consumable items which safely dispose of unrecoverable waste using a deployable drag sail. And number 5, some form of orbital fuel depot. Currently, this project is based on the European Space Agency's Odyssey project, which is still early in its development. Now, here's how the system actually works. Operators aboard the ISS will give a high-level command on the Scrapyard module. So, for example, capture a specific derelict satellite. The distributed AI then interprets these instructions and breaks them into sequential robotic tasks. The AST will rendezvous with the target, reeling it into its cargo bay and returning to an operational zone relatively near the ISS. The ASDs may then begin automated salvage tasks. Recovered material is returned to the ISS for collection and periodically returned to Earth aboard the ISS resupply vehicle, while waste is bound to a DOM and deorbited safely to burn up in the atmosphere. Once all salvage tasks are completed, the ASDs will return to standby positions, docked to the AST, which itself will dock to the ISS. The AST will require a propulsion system capable of accommodating its size and mass, given the likely travel distance and need to haul a payload. This means that it will require refueling, which is where the orbital fuel depot factors into the overall system. Now, because the ISS is a crewed environment, safety and regulatory compliance are absolute priorities. The mission follows NASA's Visiting Vehicle Safety Standards, International Debris Mitigation Guidelines, and UN Space Sustainability Principles. Of particular importance is that all salvage operations will require documented owner consent to avoid legal or ethical violations. Overall, SCRAP uses artificial intelligence systems to enhance the sustainable use of space resources, improving operational efficiency, extending mission lifespans, and transforming orbital debris from a long-term hazard into a reusable asset.
I'm Wen-Zhen, and I will go through on how the EST and ASD will see. A vision-based system, VBN, will be implemented in the EST and ASD, which they must achieve a few key objectives, including object detection, segmentation, and post-estimation. The VBN system model architecture will consist of a backbone, detection head, post-estimation head, tracking module, and LiDAR. To achieve this, we use a deep learning pipeline built on CNN, a type of deep learning that automatically learns spatial patterns in data, which is responsible for extracting meaningful visual features. Next, the detection head is tasked to process the feature maps generated by the backbone, CNN, to detect and classify objects of interest. Moving on, they are required to understand the target's pose, which is the 6 degrees of freedom of the target. We propose a hybrid CNN geometric approach for the pose estimation, combining deep learning and classical pose-solving algorithms, resulting in high accuracy. To predict the target's motion, the ASD and ASD will have a tracking module to estimate the target's velocity, acceleration, and filter out any noise in the process. This ensures them to navigate knowing the target's trajectory, improving its safety. In addition, LiDAR is implemented, which uses laser to measure distance. This method provides high accuracy measurement but has high power usage, hence it must be used efficiently. The dataset will be split into 80 training and 20 testing ratio. Training sets will mostly consist of synthetic data enhanced by domain randomization, and photorealistic rendering, while real images are used for testing. Overall, the hardware for this VBN system is feasible, but intense research and testing must be undergone.
I'm Teo Tai Chen, and I'll be continuing on with the solution. Following Wenzhen's capture system, my section covers the next critical steps: identifying valuable materials and autonomously dismantling the debris. This involves two integrated systems. First, material detection. We combine hyperspectral imaging, which reads material signatures like a fingerprint, with LiDAR for 3D geometry. Think of it like an X-ray vision and a 3D scanner working together. And we also have an AI fusion model which analyzes both sensors, and it will decide which sensor to trust in case there's a conflict of results. This determines what's valuable and what to salvage versus what to scrap before the cutting begins. Secondly, for our autonomous dismantling robot, you'll have three key capabilities. Firstly, perception. 3D Gaussian splatting creates real-time debris model that understands natural language commands. And for learning, diffusion policy learns from demonstrations, achieving 47% better performance by intelligently choosing cutting approaches based on context. Lastly, for coordination, multi-agent model allows multiple robots to work together. One cuts while the other stabilizes, avoiding collision throughout learning. Lastly, all these systems should integrate together seamlessly. Material detection identifies targets, neural motion planning calculates optimal paths, smart algorithm selects the right tool, shear cutters, rotary cutters, or grippers, with real-time force feedback adjusting during operations. This results in an intelligent autonomous system that transforms dangerous space debris into recoverable resources safely and efficiently without human intervention.
We have taken several factors into account when calculating the budget necessary for this project. Delivering the modules, the AST, and multiple ASDs may require several launches. We seek your understanding that, due to the difficulty in obtaining accurate costs, the cost estimations rely heavily on assumptions. We estimate that the total mass of the components will weigh about 12.5 tons, which is suitable for a SpaceX Falcon 9 rocket with a low Earth orbit of 22.8 tons. It is estimated that one Falcon 9 launch costs around $62 million and ESS Columbus cost US $1 billion. We assume that the cost of the scrap project will be the same as Columbus. Using Tsiolkovsky's equation and the price of two types of fuel, we estimated that the cost of fuel would be $800,000 to $900,000. Hence, the total cost of the scrap project is estimated to be $1.8 billion. Although this is magnitudes more than other active debris removal missions, those missions are temporary, meaning multiple rockets are necessary to proceed with more active debris removal. Given the prevalence of various debris around in low Earth orbit, we need a more long-term, more permanent solution. And hence, given the long-term usability of a project, we believe that the cost of a project will be less than the cost of building multiple similar rockets in the long run.